Yeah, we'll do more work. We'll do more work on exam preparation towards the end of next term as well. For next term, you'll see in the notes we've still got 3 chapters, chapters 6, 7, and 8. 6 and 7 kind of go together on the topic of polynomial congruences. And then we got a significant chapter 8 to end with on quadratic residues. It's a really nice topic to kind of finish the course with. So that'll be the work for next term. If you've looked at the examination papers already, there's a number of past exam papers available on Moodle. You'll see that they're split into 8 questions, 4 from number theory and 4 from cryptography. Each question is worth equal marks. It's worth 20 marks. But you don't have a free choice. We insist that you do 2 number theory questions, 2 cryptography questions. That gets you 80 marks. And then your 5th question can come from any of the remaining questions. Okay? So you are required to give good coverage to both halves of the course. Okay? So what you've got on the sheet in front of you is just the number theory questions from last year. This is 4 questions, and we've actually covered the material for 3 of the questions actually so far. But it doesn't always work out like that in the balance between the questions. So I guess we'll start at the start and go through question 1 and so on, see how far we go. If you've got any questions at all, anything associated with the topics that we're talking through, or anything associated with issues of exam craft or how you answer your questions, how you present your work in an exam, please do. Okay. So with having to do 5 20-mark questions in 3 hours, again, the rule of thumb, you'll have heard me say this last year, but it still applies. You've got half an hour per question, and that brings it to 2.5 hours, and so then you got an extra half hour for mopping up, so to speak, for checking work, going over time, in some places. So a half hour per question rule of thumb is a good one, and I think you'll see that that does give you plenty of time to address all the questions asked. Okay, so let's have a look at question 1. So this goes all the way back to basic matters to do with divisibility and so on. Let's have a read of the various parts, see what we have to do. Okay, a quick 3-marker at the start to get everybody started, get everybody full marks for a part at the beginning. State precisely the definition of the divisibility relation A divides B. What we started at the very beginning of the course. But you want to hit the nail on the head with that, state it very clearly, precisely. Question B, use the definition from part A to prove this important property of divisibility. This was one that cropped up all the times. We were constantly referring back to this property when we were proving kind of later things. This says that if any 2 numbers are divisible by A, then any linear combination of them is also divisible by A. Part C is to prove Euclid's lemma, that if a prime number divides a product, then it divides one of the factors in the product. And then part D. Final part is explain the main steps of how Euclid's lemma is used to prove the uniqueness part of the fundamental theorem of arithmetic. Okay. So you're not asked to prove the whole fundamental theorem of arithmetic, but just make some sensible comments and explanation of the importance of Euclid's lemma in that. Okay. So for the first part, put some handouts. Those you just get in there. These handouts. So for that first part, we want to give the precise definition of divisibility. There's not that much leeway in it. What you have to write. So A divides B, what does that mean? And the one thing you have to be looking out for here is to get the order correct. There's a potential kind of mistake you might make in mixing up the order of the relation. So here's the definition. We say that A divides B, written
as A divides B to mean that there exists an integer C such that B is equal to A times C. Okay, copy the questions there. I guess we should no, I don't think there's any extra. I guess you could put in this comment that we're only talking about integers, for integers A and B.
Okay, that's writing it out. That's pretty clear and unambiguous. We write A divides B written A slash B means that there exists an integer C such that B is equal to AC. Be very careful about mixing it up, writing A equals B times C. You know, remember it's the one on the left is typically the smaller one, the one on the right is the bigger one. The one on the left is doing just like it. And you might write it like that in plain English.
You could also write it quite compactly in kind of strict logical notation. You could say for every pair of integers A and B, you could say A slash B if and only if there exists a C such that B is equal to A times C.
Maybe you prefer presenting things, in a quite condensed way using logical statements. This one is advantageous, more compact, quicker to write down in a sense. This one has the advantage that it's more meaningful, it's easier to read, it's in our natural language. But either one is perfectly fine. Okay. Any questions about that? Or? Okay. Use your definition from part A to prove this property. Okay. If A divides B and A divides C, then for all M and N and Z, A divides the linear combination MB plus NC. So this kind of thing is a classic case of you're given assumptions, you're given a conclusion, assumptions go from the top of the page, conclusion goes to the bottom. You have to bridge the gap from one to the other by referring to either previous results or by referring to unraveling definitions of concepts that are there in the question. So we should assume A divides B and A divides C. And then down at the bottom of the page, we want to have a conclusion that A divides MB plus MC. So M and N are two integers, as the questions there we're working on. M and N are two integers. So you've got to go from these assumptions down to that conclusion. And sometimes you can, it's quicker to step backwards. How could you ever reach this conclusion? And especially since this question is just asked straight after one where we've been asked to give the definition of this relation. So we can roll that back immediately. Say, well, the only way you could make this conclusion is if you're able to write MB plus NC equal to A times something. So there's a gap here. Underline it in green. You might necessarily include that in your written submission. I'm just putting that there for our benefit here. So there's a gap there. And if I can fill that gap with another integer factor, then I'll have shown that there exists this other integer factor such that the thing on the right of the symbol is equal to this integer C times the thing on the left. The A and B and C are being used for different purposes here as regards the definition, but you have to be able to map the different things onto each other. Okay. So you've got to fill that gap. And where is that going to come from? Well, what fills that gap is somehow going to come from these statements here. These statements are divisibility statements, so they point to the existence of complementary factors as well. So we can say then there exists, what do I call them, a beta and a gamma in Z, such that
B is equal to beta times A, and C is equal to gamma times A. Okay. That's clearly true because that's the definition of the divisibility. So there exists another factor such that when you multiply it by the divisor, you get the divisee. So that's from the definition of divisibility. So then we're interested in MB plus NC, and then it's just a matter of straight substitution. So M beta A plus N gamma A, and then it's just a matter of factorization. So this is M beta plus N gamma times A. So we've reached the existence of this integer, and it certainly is an integer because M, beta, N, and gamma, they're all integers. So you multiply them and add them, you've still got an integer. It's multiplied by A, and it gives you this thing, MB plus NC. So this is your M beta plus N. So then you fill that gap, you're justified in concluding then that A divides this. That's just true by the definition of straight line. Okay. I've covered myself, covered all angles up there. Any questions to our queries? So that was worth 5 marks. It's a few more marks given for the next part. Question 7, question C, part C, worth 7 marks. Euclid's lemma states that for all primes P and for all pairs of factors A and B, P divides A times B means P divides A or P divides B. Prove this lemma, clearly state any results about divisibility or greatest common divisors that you rely on. Okay? So you're given some freedom here in that you don't have to prove everything from the ground up, so to speak. You can make use of other results from the course as long as you clearly reference them, clearly indicate that making use of this result here. So we assume P is prime. And AB are 2 integers, and P divides AB. It's good practice for your own benefit as well as the reader's benefit to just lay out very clearly all the assumptions in play. For your own benefit, because parts of these assumptions invariably will have to be called upon and to be used in your argument to do your proof. So it helps if they're actually written out in front of you there on the piece of paper that you're working on, so you have them all in front of you, rather than having to go back to the question to find them. Again, so. And can we do our trick of putting down the conclusion and try and bridge the gap? Maybe, although it's maybe not as direct or maybe not as straightforward as the previous one. See, the conclusion we're trying to get to is that P divides A or P divides B. So there's an interesting little twist in how this proof starts off, which you might not have seen in other arguments in mathematics. It's a little bit, kind of have to look at it twice, but either so first of all, we just remark, either P divides A or it doesn't. I.e., P does not divide. Yeah, that's pretty clear. It's a statement. Statements are either true or false. P divides A or P does not divide. If it so happens that P divides A, then the proof just stops here. We don't need to go and investigate B because we already have that P divides A, and the conclusion we're looking for is P divides A or P divides B. If you've already reached a conclusion, apparently for free, that P divides A, then you're finished. There's nothing to prove. There's only we only have to prove something in this case where P does not divide A. And that's a crucial extra piece of information you need in order to get the thing. Okay? So if P divides A, we're done. Nothing more to prove. So now, additionally, we assume assume that P does not divide.
And now we have to force through, we have to prove the conclusion that P divides B. But crucially, it depends on this fact that P does not divide A.
So i.e., another way of saying that is that the GCD of P and A is equal to 1.
Okay. What does that rely on? That relies on the fact that P is a prime number. P only has two divisors, 1 and P, that it can possibly share, have in common with other numbers. This statement says, well, A is not divisible by P, so the only other possible shared common divisor between P and A is 1.
So that is the greatest common divisor. And that's true since P is prime. It only has divisors. 1 and P.
And now here's the thing where we're going to refer to another result, which we don't necessarily have to prove from the ground up.
Therefore, there exists a pair of integers, m and n, such that 1 is equal to mp plus na.
Okay. Well, I've stated it clearly.
So, and maybe just put a little remark of attribution. You could say this comes from Euclid's algorithm.
Remember, when you do the second stage of Euclid's algorithm, after finding the GCD, you then run it backwards and you find the pair of coefficients that multiply the two numbers and give you the linear combination equal to the greatest common divisor. Well, here the greatest common divisor is 1. So we know there exists this pair of coefficients such that 1 is equal to mp times n.
But this comes from Euclid's algorithm, or earlier results characterizing the GCD. Even before we proved Euclid's algorithm, we were able to prove a lemma that said the greatest common divisor can always be expressed as a linear combination of two numbers. So I've clearly stated that result. I've given some attribution for it, so I can use it now. So now, see, remember now we're trying to prove that P divides B. So we got this equation here, and we multiply both sides by B. So this implies that B is equal to MPB plus NA. Sorry, I'm changing my B's there.
So here we got P. We're looking here to extract a factor of P. You can see a factor of P in that term. Okay, we don't see a P there, but crucially we see A times B. And at the top of the page, one of your assumptions is P divides A times B. So there is a factor of P in A times B that can be taken out here.
Okay. This shows P divides B, since P clearly divides MPB. Okay, you don't have to give any further justification to that, it's quite obvious. And P divides AB. And we're also here using part B. We've got P divides
These two things, therefore it divides any linear combination of them. So you take an m times, or you're taking this first term plus n times the second one. So just to review that, does that prove Euclid's algorithm? We assumed P divides a product A times B. It may happen that P divides A, in which case, fine. P divides one of the factors. But it's only in the case that it doesn't divide the first one, then we must prove that it must divide the second. Okay. If it doesn't divide either of them, then Euclid's lemma will not be true. So we take on this additional assumption that P does not divide A. It's co-prime to P and A are co-prime. Therefore, we can linear combination them to get 1. Multiply that both sides by B, and this expression here is clearly divisible by P.
from assumptions and earlier results, and so therefore P divides U. So this shows, I mean, you don't necessarily, I think, just stop there. That'll be fine. This shows that P divides A or P divides U. It can't happen that P does not divide, well, it doesn't divide A, it must divide. Is that okay? Any questions about that? Yeah, and I put a little bit more effort into explaining that. It was worth a few more marks, worth 7 marks. Then part D, if you look at that, part D is asking, explain the main steps of how Euclid's lemma is used to prove the uniqueness part of the fundamental theorem of arithmetic. That is, if an integer n can be written as n is a product of p's or n is a product of q's, where the pi and qj are primes, then these two factorizations must be essentially the same. There's 5 marks going. It's not asking like for a full, complete proof. It's just asking for explain the main steps. So to explain the main steps of this, you could say this is proved. Yeah, by induction on the number of factors in any one of the products, or the products of p's and the q's, they could potentially be different. So the base case is n is equal to 1 prime, which is also equal to 1 prime p, which is equal to 1 prime q. Well, there's nothing to prove. Are these two prime factorizations unique? Yeah, it has to be. If the number is a prime itself, clearly there's only one way to express it as a product of primes. Okay, you can't magically have these p and q be different because they're same, because they're equal. Okay? So nothing to prove here. The factorizations are the same. No, actually, so then for the induction step, if n, so here is where we adopt the we can't see it. Sorry. It's where we adopt the general setup. Here, so here we have two potentially different prime factorizations, P1 up to PR times Q1 up to QS. So clearly P1 divides N. So that implies that P1 divides this product, Q1, Q2, up as far as QS. Well, that implies that by generalizing Euclid's lemma from before, said if a prime P divided a product of two things, then it must divide one or the other. Here we got a prime P dividing a product of S things. Well, by extension, if it divides S thing, the product of these S factors, it must divide one of them. Okay. So that's from the extension of Euclid's lemma. Without loss of generality, we can assume j equals 1.
If need be, we can just relabel these factors over here. So just assume that this P1 is equal to the Q1. Move things around if the P1 is in the middle somewhere. Bring it out to the front.
So that implies, well, okay, P1 divides Q1, but that implies P1 equals Q1 as Q1 is a prime. P1 and Q1 are prime. Okay, so primes only have two divisors, themselves and 1. But P1 and Q1 are both primes, so neither of them is 1. They both have to be at least 2, larger than 2. So if P1 is dividing Q1, it has to be equal to Q1. Okay, so that's the only factor, the only non-trivial factor that Q1 has. This itself, because it's a prime number. So that implies that this integer n divided by P1 now has a prime factorization.
Now has two possible prime factorizations, P2 up to PR and Q2 up to QS.
This is clearly another integer.
With supposedly two prime factorizations. But now these prime factorizations are shorter. So they're covered by the induction hypothesis.
So these are shorter factorizations, hence covered by the induction hypothesis. So they are the same. That's the result we're proving, that the two possible factorizations are the same.
So therefore, these two must be the same. So R must be equal to S, and the primes listed in the product here must be exactly the same as the primes listed in the Q product.
So R equals S, and PI equals QI for all I now between 1 and R equals S.
Okay, the induction hypothesis will say all the P's are equal to all the Q's for every index from 2 up to R. And we've just concluded that the first ones are equal. So therefore, they're all equal.
So I think that's the main.
That kind of addresses the question, I think. Explaining how Euclid's lemma, so it's used here, right here in the middle. The main steps in showing how that is used to prove the uniqueness part of the fundamental theorem. So it's now 10:30. So I was able to do that in half an hour with all the explanations and all the extra explanations. So if you're on top of your stuff and you know your stuff, I think and you're working in exam mode, you won't be taking the time to explain it to other people as you're writing it out. Well, you can do it to yourself, so it's still a good thing to do. I think it's a good question.
Any queries or questions about it? Okay. So question 2 is about congruences. And question 3 is about prime numbers. It's a little bit, the order is chopped and changed around from the order in which we consider them in the course. Let's do the congruences one. You guys everybody got that? So again, please do stop me at any point if there's questions you want to ask. So 2a, again, kind of similar start to this. Carefully state the definition of the congruence relation. How does this relation relate to the remainders left when a and b are divided by n? Okay. So again, we say a and b are congruent modulo n. Yeah, this written as a congruent to b modulo n.
So when do we say that? That's the definition. What do we need to see in order to say that? We need to see that n divides the difference.
Exactly when n divides the difference a minus b.
Okay, so that's the definition we supplied.
You can define it in logical symbols a little bit more compactly, maybe.
That's one thing that doesn't give is it doesn't give you the English version of what the thing is called or how you read it in English, how you actually speak it. So maybe the English version is slightly practical. One other thing we might also say is we only ever do this thing for any integer n not equal to 0. So we never talk about things being congruent. Do we? Well, you can talk about things being congruent. 0, but then 0 only divides 0. So yeah, okay, that's a minor point. But if you don't deal with that point, you won't lose any marks. It's just the case with. Oh yeah, and then there was this extra little part. How does this relation relate to the remainders left when a and b are divided by n? So a being congruent to b modulo n, how does that relate to integer division by n? Just stated here, if and only if a and b leave the same remainder. So the remainders have to be the same. Same remainder when integer divided by n. So I do like, when you look at the past exam papers, I do like to test the definitions of these fundamental things. The divisibility relation, the congruence relation, things like that. I mean, it's crucial to be able to give clear, precise definitions of it, because everything else is built on top of those definitions. Part B says clearly state the definition of the Euler Toschen function and prove for any prime p in positive integer n, the Euler Toschen function satisfies. So that's the product formula for a single prime power. So we can say the function phi is defined by, well, phi of n equals the count of the integers I satisfying. So we're talking about the ones between 1 and n, and GCD of I and n is equal to 1. So it's the count of all the numbers up to n that are co-prime to n. Yeah. And there's 8 marks going for this part. If I wanted to display my understanding fully, I'd also say this about it. This is quite an important fact about it. This is the order of the group of congruence classes modulo n under the operation of addition, of multiplication. i.e. phi of n is the size of Zn
So we'll look out for it. Okay, so the proof part is to prove that phi of the power of p is equal to this expression here.
It says n in the question. We're going to switch to m just not to confuse it with this n that's mentioned there. So how did we prove this? So this is like the base case of the induction proof of the whole product formula for phi. So this is the base case, just where the argument for phi is a single prime power. And we proved this by just a careful counting according to the original definition. Okay?
So we need to identify the integers in the list. So we need to consider everything between 1 all the way to p to the m.
So this big long list of integers
That we identify the integers in this list that are co-prime to p to the m.
Or alternatively, we can count the ones which are not co-prime. Here's all the integers. We want to count the number of ones that are co-prime. So alternatively, count the ones that aren't co-prime, and then however many is left is the answer.
Well, so we can say the divisors of p to the m are exactly. So what possible divisors does p to the m have? Well, it only has 1 p squared, etc., up as far as p to the m.
Okay, because it's a prime number.
Since p is prime.
So the only possible factors that you can see in a power of a prime number are just the various smaller powers. Yeah, everything from 1 up to p to the m.
So an integer n is co-prime to is not co-prime to p to the m if and only if p divides n.
If an integer n has a factor of p in it, then it is not co-prime to p to the m, because their greatest common divisor will be at least p. And if there are no p's in n, it will be co-prime to p to the m. Okay? Because the only factors that p to the m has to possibly share with any other numbers are just various powers of p. So if there's no p at all in n, you are co-prime.
The integers from the above list that are co-prime, or that are multiples of p, that's what we've changed to now, are exactly, so you start listing multiples of p. So you go 1p, next multiple of p is 2p, next one is 3p. So you're just listing every multiple of p. We're trying to list the ones out of this list here.
So how many of these multiples of p fit into this list? Well, it ends with the very last number on that list is a multiple of p.
So it ends with the last one is p to the m minus 1 times p. We'll stop.
That's the end of the list. There's the original list of integers, everything from 1 to p to the m. These are all the multiples of p that are in that list. Those are all the ones that are not co-prime to p. So the remaining ones are.
So the elements remaining in the original list i.e. not in this list, are the ones co-prime to p to the m. Therefore, 5p to the m is the number of things in the original list, which was p to the m, minus the number of things in this list, and there's p to the m minus 1
numbers in this list, because they're written in such a way that they're counting themselves. You go zero. Sorry, what am I doing? 1 is not a multiple of p. 1 is not a multiple of p. 1 remains. So here they're counting themselves 1, 2, 3, 4, 5, 6, and it ends with p to the m minus 1. So p to the m minus 1 is the count of the number of things.
That's the expression, and that factorizes as p to the m minus 1 into p minus 1 as required. So you see, it's not too hard. We're just basically describing that counting.
Yeah.
So don't be afraid to just write things in normal English in your exam answers. I mean, when I put down work, it tends to come out quite Englishy, quite prosy. I'm not saying you have to do it that way, but very often, you know, people can be struggling to compactify something and say it in symbols. And it's just easiest to write out a sentence or two and say the same thing. As long as you're being precise and rigorous and mathematical, that's
Mathematics. Okay. So don't be afraid to write out and explain things if that's the best way to do whatever you're doing. Okay.
Last part then, part C, was an exercise about finding remainders of large powers. So this is the kind of thing you're asked about in one of the coursework questions at the moment. And so here we got to show the remainder left from 2017 to 1975 is divided by 14. So we need to find R, where 2017 to the 1975 is equal to something times 40 plus R. And R is between 1 and 39. Sorry, between 0 and 39.
Why are we using 1975?
Like the band?
Sorry?
Oh, I just really said you like the band.
There's a band called 1975. That's when I was born.
1975, right here.
So that's equal to Q40 plus R.
So in other words, we need the smallest positive R satisfying 2017, 1975 is congruent to R modulo 40. What is 2017? Congruent to modulo 40.
We need to simplify the base first of all. That is the base simplify when you divide
40, therefore 40 goes into 200, 201 5 times, remainder of 1. Sorry, it's 50 times. 50 times 40, remainder 1, and then so the remainder is 17. All right. Yeah, that's okay. So this implies, so we're looking for R now. R is congruent to 17 to the 1975. Modulo 40. And we can use, in order to simplify the exponents, we need phi of 40. So phi of 40, the prime factorization is 2 squared times 5. So the phi value is reduced to the power of 2 by 1. You get an extra factor 2 minus 1, but that's only 1. And you get an extra factor by 5 minus 1, which is 4. So that's 8. So the phi value of 40 is 8. And Euler's theorem, we should carefully state the results we use. Euler's theorem implies that 2 to the power 8 is congruent to 1 modulo 40. Sorry, 17 to the power 8. Anything to the power 8 is congruent to 1 modulo 40. If it's co-prime to 40, 17 is. And so we break down 1975 modulo 8. Okay? Sorry, why don't you stop me when I write something silly? Sorry, it's 8 by 5, isn't it? Yeah, so 2 cubed. So this is 2 squared, so that's 16.
Oh.
So 17 to the 16 is congruent to 1 modulo 40. Yeah? Is that right? Yeah. So we got to break down 1975 modulo 16. So we got to divide 16 into 1975. It goes once, remainder 3. To 37 it goes twice, 52, and 5, and 55 it goes 3 times 48, remainder 7. So 1975 is congruent to 7 modulo 16. So the R that we need is congruent to 17 to the power 7 modulo 40. So we've significantly simplified the original problem. It's now no longer 2017 to 1975. Now we just need 17 to the power 7. Right? So just a couple more multiplications will get that out. Okay? Square 17, reduce it modulo 40, then square the result again. Will get you 17 to the power of 4, and reduce it, and then multiply it by 3 more 17s. Okay, so just a quick work with calculator. You can quickly calculate 17 to the power 7. Okay, I just don't have time to do that. And so we've been able to avoid dealing explicitly with large integers. The largest integer we'll have to deal with here is just 17, just something a little bit into the hundreds, a little bit larger than 14. So we can work out those powers and reduce them. Okay, I better finish there. Wasn't too bad. Got through 2 questions. Do some more work with some of them in the tutorials this week, so I'll be seeing you on Friday for a tutorial. So,